You know that feeling? You're watching a video, and suddenly you're staring at that spinning wheel of death. What is actually going on behind the scenes? Well, today we're going to pull back the curtain. We're going to follow one single tiny data packet on its perilous journey across the internet to really understand what causes all that lag and delay.
You click a link and then nothing, just waiting. It totally feels like your request got stuck in some kind of digital traffic jam, doesn't it? Well, guess what? That's not just a feeling, it's actually an incredibly accurate way to think about what's happening.
So let's meet the hero of our story, one humble data packet. See, everything you do online, I mean everything, from loading a web page to sending a message, gets chopped up into thousands of these little guys. Their journey from a server somewhere out there to your screen is what makes the internet, well, work. And that journey begins at its very first major checkpoint.
And that first stop on its trip is probably right in your own house. It's a router. Now, the best way to picture a router is to think of it like a massive, super busy highway interchange, or maybe a giant mail sorting facility. It's the very first place where things can really start to slow down.
So, before our packet can even dream of hitting the open road, it has to get past two bouncers right here inside the router itself. We call these the processing delay and the queuing delay, and they're basically the gatekeepers of the network.
First up is processing delay. This is like a quick security pat-down and a passport check. The router scans the packet's header, checks it for any obvious errors, and figures out exactly which exit to send it to next. The good news is this part is incredibly fast. We're talking just a few microseconds. It's barely a blip on the radar. But after that quick check, our packet runs smack into the queuing delay. And yeah, it is exactly what it sounds like. It has to wait in line. If the router is already busy sending a bunch of other packets out the same way, our little guy gets put into a waiting room called a buffer. And how long does it have to wait? Well, that's the million-dollar question. It completely depends on how congested the router is. It could be in and out in a flash, or it could be a long, frustrating wait. All right, so our packet got its passport stamped, it survived the queue, and now it's finally ready. It's time to merge onto the actual physical link, the fiber optic cable, the copper wire that's going to carry it to its next stop. This is it. Welcome to the digital highway.
And this brings us to two of the most commonly confused ideas in all of networking: transmission delay and propagation delay. I know, they sound super similar, but they describe two completely different parts of the trip. Just remember this: one is about getting onto the highway, and the other is about traveling down it.
So let's talk transmission delay first. This is just the time it takes the router to push all the bits of our packet onto the wire. The math for it is L divided by R. L is just the length of the packet, and R is the bandwidth of the link. Let's use our highway analogy. Think of bandwidth as how many lanes the on-ramp has. If you have a really big packet, say a long convoy of trucks, or a very narrow single-lane on-ramp, that's low bandwidth, it's going to take longer to get everyone onto the main road. That's transmission delay. Now, the moment the very first bit of that packet hits the wire, a different clock starts ticking. This is propagation delay. This one is simply the time it takes for that bit to travel the physical distance of the link. The formula is D for distance, divided by S for speed. And this speed is a physical constant. It's pretty close to the speed of light, around 200 million meters per second. So this delay has nothing to do with how wide the road is. It's all about the highway speed limit and how long it is.
And this is absolutely crucial to understand. Let me say it again. Propagation speed, S, is the speed limit on the highway. Bandwidth, R, is how many lanes the highway has. They are not the same thing. You could have a massive 20-lane superhighway. That's amazing bandwidth. But if that highway stretches all the way across the country, it's still going to take time to drive from one end to the other.
Okay, so we've now seen the four individual obstacles our little packet has to deal with at just a single router. Let's put them all together and see what the total time penalty looks like for just this one stop.
And here it is. The total delay at one node, or one stop, is simply the sum of those four parts: processing, plus queuing, plus transmission, plus propagation. But here's the kicker. That's for one stop. To get from a server in California to your computer in London, a packet might have to hop through a dozen or more of these routers, and it accumulates more and more delay at every single one.
This chart sums it all up perfectly. Processing delay is tiny, pretty much negligible. Propagation delay depends on physical distance. It can be small for a local network, but huge for a satellite link. Transmission delay really hurts on slow connections. But just look at queuing delay.
Its duration says it all, varies with congestion. That's the real villain of the story. It's the wild card. It's the source of almost all unpredictable lag. This is what makes your video call stutter. It's that unpredictable traffic jam.
So far, we've only been talking about delay. Our packet, even if it's slow, eventually makes it through. But what happens in the worst-case scenario? What happens if that traffic jam at the router becomes a complete, total gridlock? Remember that buffer we talked about, the waiting area for packets? Well, it's not infinite. It's not a magical holding dimension. It's more like a real-world waiting room. It only has a limited number of chairs. It can only hold so many packets at one time. So, in a normal situation, our packet arrives at the router sees an empty spot on the buffer, and our packet dutifully gets in line. It might experience some queuing delay, for sure, but it's safe and sound, just waiting for its turn to go.
But if our packet arrives at a moment of intense congestion and that waiting room is completely full, there's nowhere for it to go. The router has no choice but to simply discard it. It drops the packet. This is packet loss. It's the digital equivalent of being turned away at the door because the club is already at full capacity.
Now, the internet has clever ways to deal with this. The original sender will eventually notice the packet never showed up and will probably send a new copy. But here's the crucial point. Our original packet's journey has completely failed. All the energy and time and resources that it took to get it this far, completely wasted.
So just think about that for a second. Every single piece of data you send or receive gets shattered into thousands of these packets. Each one has to independently navigate this chaotic landscape of different delays, all while facing the constant threat of just being deleted entirely. Which leaves us with a pretty fascinating question, right? How on earth does a system built on this much potential chaos manage to deliver our videos and our messages so reliably? Well, that is a story for another time.